Hello, and thanks for your continued interest in the subject of shaft alignment. This tutorial will discuss the 8 basic steps of shaft alignment that will hopefully assist anyone who is responsible for installing or maintaining rotating machinery, such as motors, turbines, pumps, fans, gears, compressors, and generators, for people who evaluate the operational or mechanical performance of machinery, and for technicians and engineers who are responsible for rotating equipment. So this information is intended for trades personnel, maintenance supervisors, training instructors, mechanical procedure writers, vibration analysts, engineers, maintenance managers, and any interested operations personnel. This tutorial is principally intended for anyone who has never tried to align machinery before but has a desire to learn how to do this deceptively simple task. For those of us who have done this before, it is very easy for us to forget how difficult it was to learn how this is done. For someone who is just starting, it would be natural to wonder, okay, is there some sort of a step-by-step procedure that I should go through so I don't make a fool of myself, or worse yet, damage my company's machinery, or even worse yet, get someone hurt like me or my coworkers? So yes, there is a process to this. What I've tried to do is identify the 8 major steps to aligning rotating machinery, which we will discuss in this tutorial. I'm sorry, what's your question? How long is this going to take? Sure, good question. My answer is, how much are you willing to learn and how deep do you want to get into this? At this particular point in time, I've been aligning machinery for about 31 years, and I still consider myself to be a student of this subject because every time I work on a drive system, I always learn something new. The first step in the process is to get some training and some tools you're going to need. The key ingredient is to get whoever is going to be involved in the alignment process adequately trained on all the various alignment procedures and techniques, how to care for delicate measuring instruments and how to use them, what tools should be used to reposition the machinery, whether a machine is really ready to be aligned and operated or whether it should be removed and rebuilt, when a base plate or foundation has deteriorated to the point where repairs are needed or corrections should be made, correcting problems that exist between the underside of the machine case and the points of contact on the base plate, how to check for static and dynamic piping stress, what the desired offline machinery positions should be, how to measure offline to running machinery movement, what the alignment tolerance is for the machine they are working on, and how to keep records of what was done during the alignment job for future reference. Bear in mind that the information contained in this or any of these tutorials or any of the reference materials is not taught in any kindergarten through 12th grade educational system. So, expecting a high school or college graduate to know how to perform an alignment job is unrealistic. The burden of training personnel to understand and apply this body of knowledge falls on the employer and the companies who own and operate their machinery. If you are hiring outside contractors to do this work, are you certain that they have been trained and certified? For someone who has no experience in machinery alignment, it is recommended that somewhere between 24 and 40 hours of non-product specific classroom training be completed. Additionally, it might be wise to give them the opportunity to practice alignment on simulation training devices rather than production machinery. After the classroom and simulation training has been completed, it is suggested that the individual who attended the course perform an alignment job on a process drive system within a short period of time just to reinforce what they have learned. Someone who is experienced in aligning machinery should oversee the trainee and enforce the material taught in the course with on-the-job training. Since there are a wide variety of alignment techniques that need to be learned, one field alignment job is not going to be sufficient to learn every method. The progress of each individual should be tracked as they become more knowledgeable in this field of endeavor. Once a person becomes proficient in each level of knowledge, they should consider getting certified at their level of proficiency. Once a person has performed each one of the 5 basic alignment measurement methods at least twice, they typically get a pretty good grasp of the material in Category 3 alignment. On the average, it takes about 2 to 5 years for someone to become proficient at a Category 2 to 3 level of machinery alignment, assuming they encounter alignment tasks about every 2 months or so. Knowledge and experience at the Category 4 level can take much longer. Okay, so you are going to go out and align some rotating machinery today. What should you know about the drive system before you attempt to align it? Shown here is a sample machinery data card for a simple 2-element drive system. This will hopefully give you an idea of what might be helpful to you. This is the front side of the machinery data card. There are 4 major blocks of information. At the very top is the name of the machinery and where it is located. The next block down is a photograph and a sketch of the drive system showing dimensional information that you will need in correcting a misalignment condition, like where the bolts are at and where the shaft measurements should be taken. The next block of information is all about the driver machine. Is it a motor or a turbine or an internal combustion engine? What's the model number and serial number? What's the horsepower and speed? How much does the whole unit weigh? How much does just the rotor weigh? What is the trip speed? Are there any critical speeds? What type of bearings are in the machine? What are the radial bearing clearances? What type of lubricant should be used and how much? How far and which way does the shaft move from offline to running conditions? What wrench size do you need to loosen the foot bolts? The final block of information is all about the driven machine. Is it a pump or a compressor or a fan or a gearbox or a generator? The rest of the information is similar to the information for the driver, like the model number, bearing information, etc. This is the backside of the machinery data card. There are 3 major blocks of information here. The uppermost block is information on the coupling. What type is it? Who is the manufacturer? What's the model number and serial number if it has one? What is the outside diameter of the driver and driven shafts? Are the shafts straight or tapered? Is there an interference fit? If so, what is the amount of interference? Does the coupling require lubrication? If so, what kind and how much? What is the coupling bolt torque? The block of information in the middle is the alignment information. What is the recommended alignment measurement method? What are the shoot-for readings? What saw foot and final correction shims are currently under the machinery feet? What is the desired offline vertical and lateral shaft positions? The block of information at the bottom of the sheet is historical information. When was the drive system installed? What maintenance or repairs have been done on the machine, and when were they done? Simple and straightforward. All the information you need on one piece of paper. What appalls me is that just about every plant I go into, either no one has this information in one place, or they have some of it scattered here and there, but in many cases, they don't have any of this information. Prior to working on rotating machinery, make sure all safety precautions have been followed. Go through a lockout, tagout, tryout procedure. Inform the operations personnel what machinery you will be working on before you go out, and let them know when you have finished your work. If you are working on an electric motor, where is the local disconnect switch? Is it labeled correctly? Once you disarm the disconnect and hang your safety tag on it, then try to start it. Won't start? Good, you did it right. If you're working on a centrifugal pump, is there a possibility of the pump rotating backwards if the suction and discharge valves are open? If you're working on a fan, is there a possibility of the fan rotating if the dampers won't close all the way? In other words, think about all the possible things that could go wrong and stop them from happening. In my opinion, the next 3 steps are the core part of the alignment job. This is perhaps the most overlooked step in the alignment process and possibly the most important one. Here is when you perform bearing clearance or looseness checks, measure shaft or coupling hub runout, inspect the coupling for any damage or worn components, find and correct any problems with the foundation or base plate, find and correct any softfoot conditions, find and eliminate any excessive piping, conduit, or ductwork stresses on the machines. The vast majority of people who align rotating machinery skip this step. Then they start having problems later on when trying to align the machinery, only to discover there is one or more than one problem mentioned here that was causing them their grief. There is an entire training tutorial devoted to performing these preliminary checks, so I won't dwell on this here. First, rough align the machinery and ensure that all of the foot bolts are tight. Then, measure the shaft positions using measurement sensors within an accuracy of 1/1000th of an inch or better, such as dial indicators, laser detectors, proximity probes, optical encoders, charge coupled devices, or linear variable differential transformers. From these measurements, determine if the machinery is within acceptable tolerances. If the machinery is within acceptable tolerances, skip the next step. If they are not within acceptable tolerances, go on to step 6. If the machinery is not within acceptable alignment tolerances, first, determine the current positions of the center lines of rotation of all the machinery. Then, observe any movement restrictions imposed on the machines or control points. Next, decide which way and how far the machinery needs to be moved, and finally, go ahead and physically reposition the machinery in the vertical, lateral, and axial directions. Each time you make a move, be sure to check the alignment as described in step number 5 to determine if the machines really moved the way you hoped they did. If you are within acceptable alignment tolerances, go on to step number 7. If you are not within acceptable alignment tolerances, then you need to repeat this step. When the final desired alignment tolerances has been satisfied, record the final alignment position for future reference. Keep a record of the thicknesses, shapes, and orientation of the softfoot shims, as well as the final shim packs used to adjust the height or pitch of the machinery. If lateral and axial jack screws exist, touch each jack screw against the side of the machine case, then draw them back out so there is a 10 to 20 mil gap between the machine case and the tip of the jack screw. Then lock the jack screw in that position and make sure the foot bolts are secured. Again, this is just a broad overview of what each step is in the alignment process. I realize that some of what I mentioned here may not make any sense, or you're just not sure what I'm talking about. All of these tasks will be covered in greater detail in several of the upcoming tutorials. What you're doing here is making sure that the drive system is really ready to run before you remove the safety tags. Make sure the correct type and amount of lubricant is in the bearings of all the machinery in the drive system. Ensure all the foot bolts are tight. If you replaced an electric motor, you may want to temporarily remove the disconnect lockout tag and ensure the motor is rotating in the correct direction, and determine where magnetic center is if the armature is supported in sliding type bearings. If you were working on a steam or gas turbine, you may want to perform overspeed trip settings. With the driver disconnected from the driven unit, now might be a good time to measure vibration levels on the bearings. After the driver's solo test runs are complete, install the lockout tag again. Make sure the shaft end to shaft end distance is correct for the coupling. Assuming the coupling was inspected for damaged components during the alignment job, replace any defective parts, reassemble the coupling, and check for rotational freedom of the entire drivetrain if possible. Make sure any connections like piping or wiring or ductwork attached to the machinery is secure and not inducing any stresses. Install the coupling guard and make any final checks on a drive system prior to removing the safety tags. Now, if everything looks ready, cross your fingers and let's start the machine up. Operate the unit checking and recording vibration levels, bearing and coupling temperatures, bearing loads, flow rates, suction and discharge pressures, current draw, and other pertinent operating parameters. If the vibration levels are low and the bearing temperatures seem normal, then this is a good time to capture what is called baseline performance data. If the vibration levels are high and or the bearing temperatures are higher than you'd like to see, and you know that you did the alignment correct, then the high vibration or high bearing temperatures are due to some other problem than a misalignment condition. Now, I'm sure you realize that it is quite possible for the vibration to increase on a machine after you've aligned it, right? Pardon me? You didn't know that. You better go through the tutorial on vibration on misaligned machinery to explain how and why this can happen. Here's a question that I get asked all the time. Hey John, how long is this going to take? Well, a lot is going to depend on what the size of the machines are that we are going to try and align. What I've tried to do here is show how long it would typically take to align a small, medium, or large drive system. The first two steps we looked at, getting the training and tools you need and gathering the information that will help you, can take months or even years to finish and should be completed before trying to align any drive system. The first physical step in the process is safety tagging and locking out the machinery. Depending on the complexity of the drive system and its controls, lockout, tagout procedures will take anywhere from 30 minutes to several hours to complete. It may end up being the best time you ever spent, unless, of course, you prefer to spend your time in a hospital or eternity someplace else. For the preliminary steps, it can take anywhere from 2 hours to 2 weeks, depending on what you find and how committed you are to fixing the problems. Regardless of the type of measuring instruments and associated tooling you use, it's going to take somewhere between 15 minutes to an hour to mount the alignment fixtures on the shafts, set up the instruments, rotate the shafts to capture a set of measurements, determine your misalignment condition, and calculate your alignment deviation. Make sure you get accurate measurements, since how you plan on correcting the misalignment problem you find depends on how accurate your measurements are in this step. If you plan to learn how to do alignment graphing or modeling, the first time you try to construct an alignment model, it will probably take you about 20 minutes or so, and you're not sure you did it correctly. After you've done 3 or 4 alignment models, you get the hang of it and will probably take you 5 minutes or less. Deciding what moves you're going to make doesn't take much time once you know where the shafts are at, what the boundary conditions are, and where you want the shafts to be when offline. But if you make a bad decision here, it could mean the difference between spending 2 hours or 2 days aligning your machinery. Okay, so now you want to add 100 mils of shims under the outboard feet and 40 mils of shims under the inboard feet of a 20-ton steam turbine. You know, talking about that and doing it are 2 different things. If you're talking about adding those shims under a little 100 horsepower motor, it's going to take you about 15 minutes or so. If you're talking about adding those shims under a 20-ton steam turbine, it's probably going to take about 4 to 6 hours. Take a moment and look at the graph. I don't know about anybody else, but the majority of time I spend in an alignment job is performing the preliminary checks and positioning the machinery. As we have discussed, there are 8 basic steps to the process of aligning rotating machinery. No step is any more important than any other, and it is recommended that no steps be skipped. The very first step in a process deals with tools and training. Over the past 25 years, there have been slightly over 3,500 people attend our training courses, and about half of them have since retired. In the introductory tutorial, I talked about who should be responsible for alignment of rotating machinery. In too many industries, the full responsibility of machinery alignment rests solely on the shoulders of the trades personnel. But foremen, vibration technicians, engineers, and managers have a role to play too. Shown here is some employment information from the United States Bureau of Labor Statistics. Although everyone employed in the listed occupations probably won't be working with rotating machinery on a daily basis, this gives you an idea of who will probably be exposed to rotating machinery sometime in their careers. As a mechanical engineer myself, I'll be the first one to admit that I was never taught anything about shaft alignment in college. Most of the people I've worked with in industry weren't taught this in their schools either. So the burden to learn this is on industry and the individuals themselves. You know, if you seriously think that purchasing an expensive alignment measurement system that does the thinking for you is going to solve all your alignment problems, you are deluding yourself. You really should consider getting some training that goes beyond what your alignment measurement system supplier gave to you that only trains you on and promotes their particular product. You don't have to have a lot of money to do this right. I know people who use alignment brackets they made themselves and dial indicators they bought for about $100 that are far better at alignment than other people I know who are using a system that costs $10,000 or more. Additionally, just because someone went to an alignment training class or listened to all of these tutorials doesn't mean they understood the material. The best way to prove that you know what you are doing is to get certified in that subject material. You know, if there were only a dozen or so rotating drive systems in existence, I probably wouldn't say anything about this. But how many pieces of rotating machinery are within a 500-mile radius of where you are at? How many pieces of rotating machinery are in North America? When you are asked to install and align machinery, it is very helpful to have information that will assist you in understanding the machinery you are going to install with a clear picture of what your alignment goals are. If you do not have information similar to what was contained in the machinery data cards, then the best way to approach this is to start gathering it one machine at a time. As I mentioned, the most overlooked step in the alignment process are the preliminary steps. I am as guilty as everyone else by skipping some of these steps. Every once in a while I get lucky and get away with it, but not often. Based on my experience working with thousands of drive systems in a wide variety of industries, it appears that 80% of the machinery has a software problem that is bad enough to warrant correcting. Finding and correcting the items we discussed in the preliminary steps is covered in greater detail in another tutorial, so I strongly recommend that you learn what these problems are and fix them before you try to align your machinery. Getting good alignment measurements is vitally important, but knowing what the measurements mean and how you are going to use the measurements to correct a misalignment condition is extremely important also. Remember what was said in step 6? First, determine the current positions of the center lines of rotation of all the machinery. Then, observe any movement restrictions imposed in the machines or control points. These movement restrictions are also known as boundary conditions. Boundary conditions describe realistic physical limits of movement on the machinery. An example of this would be that you, or your alignment measurement system, decided that a motor needs to move downward to align it to a pump, and there are no shims to remove under the motor. In situations like this, I have seen seemingly intelligent people remove the motor and grind the base plate away. That is insane and definitely unnecessary. Another tutorial will cover and discuss boundary conditions in far greater detail. I also strongly recommend that you do not use vibration analysis as a determining factor to ascertain whether your machinery is within acceptable alignment tolerances. Another tutorial will discuss the relationship between misalignment and vibration and why much of what you think might happen to machinery when it is misaligned may not necessarily be true. Well, hey, thanks again for your interest in machinery alignment, and I hope this information has prompted you to want to learn some more.